So hello friends, welcome back to digital communication tutorial. So here we will see, in the previous video we will see what are orthogonal signals. Now here we will see the probability of error calculation in the orthogonal signals. So here is the thing, in the previous video I have shown you the receiver part and also the signals, how they are arranged in the dimensions. Okay. So here is the thing, whenever we are calculating the probability of error, first we need to calculate first it is easy to calculate for the probability for the correct symbol. Okay, so I'll say S1 is the signal. Okay, S1 is the signal which I sent. Then what happens is I have a correlation vector. Correlation vector is the thing which I'll match after getting the output, whether whatever output I got is without noise or with noise. Okay, that I need to check. For that thing I'll consider a correlation vector here. The S1 is the symbol I sent. UTS plus N1, N2 up to Nm. These are the values of the correlation vector. Okay. Now I'll consider whenever I consider this correlation vector, and I need to consider probability CS. CS is the correct symbol probability. Okay. How will I get correct error symbol probability is I'll minus it with the 1, then I'll get the error symbol probability. Okay. For error symbol there is another method continuation for this. Okay. Like we can approximate it to some value after getting it. Okay. Let's see how it goes. Now for probability of correct symbol, it should be probability. This is, you consider it as a random probability, random probability theory. Okay, then it should be N2 less than C1. Okay, C1, what is C1? C1 is the correct symbol which I got. This is the correlation vector. The first thing, do TS plus N1. It has some noise, let's do TS. Okay, whatever N2, that should be less than C1, that should be less than N3, should be less than C1, Nm should be less than C1. Why it should be less than C1 is C1 should be of high strength, because whatever I shown in the receiver part, high strength only takes a high strength signal will only be allowed for the decision. So if C1 is higher than all the things, then it considers the C1 part. So here after getting the probability function, after getting the probability, we get the probability density function like this. Okay, this is 1 minus q C1 by root n naught by 2 n power minus 1. This is my probability of correct symbol with a random variable of C1, with a variable of C1. Okay, so this is a probability density. Now when it comes to the random probability, we get the output by taking the input value and also probability density function. Okay, so this is the probability density function I am considering, and whatever input is my correlation vector PC1. Okay, that I am expressing it as a Gaussian distribution function. Okay, this Gaussian distribution function into my probability of correct symbol, I integrate it with minus infinity to infinity with respect to the C1. Then I'll get probability of correct symbol. That probability of correct symbol, I'll minus it from 1, then I'll get the probability of error symbol. This thing is numerical evaluation. It's hard to do it here on the board. So it is approximated to some value. I'll tell you what is the value. Okay. So let's start dealing with the next thing. So you can see here the bit error rate is given by k by 2 times PS, probability of symbol. So for equally likely probabilities, we have PES by m minus 1, okay, where m is what? Number of signals, PES by 2k minus 1. K is a constant which is defined to be log 2 m. Okay, so we get the probability of error here, bit error, k by 2 times PS. Now this is the graph showing the improvement of SER with respect to the number of addition of bits here. Okay, as we add on bits here, probability of signal to error, probability of symbol error rate is increasing, but only the backdrop is here. Bandwidth is decreasing. I mean bandwidth is doubling for every bit. Okay. Now the other last thing to conclude about this orthogonal signals is that why does SCR drop as m increases? That means whenever dimensions are increasing, why SCR is decreasing. Okay, so we know that what is the distance here? It will be 2 log m2 e. Okay, this is the distance here. Now what happens is here, since d square increases linearly with k, that means if I say d square equal to 2k ab, log 2m is k here. Okay. The pairwise error probability decreases exponentially with k, the number of bits per signal. Okay. So what is this k? This is number of bits per symbol. It is number of bits per symbol. What happens is this error probability, it decreases with increasing m. So offsetting this to m minus 1 of neighbors at any point, m minus 1 ways of getting it wrong. So m increases exponentially with k. What happens here is m increases exponentially with k. Okay, which affects what happens. So whatever these two fractions are there, they are falling into the union bound. Okay, so this is the main backdrop of the orthogonal signals. Okay, so this is how we calculate the probability error. That's all for this video. Thank you.